Welcome to today's session on precision maintenance. My name is Santosh Raikar, and today we're going to explore a fundamental shift in how we approach reliability. Instead of just reacting to failures, we're going to learn how to stop installing tomorrow's failures today. By focusing on the fundamentals, foundations, alignment, balance, and cleanliness, we can move from just getting machines running to ensuring they stay running through a rigorous process of measuring, correcting, verifying, and documenting. There is a common tension in reliability, the difference between a machine that starts and one that is actually reliable. A machine can meet production targets at handover while still carrying hidden killers like internal strain, contamination, or residual unbalance. We must realize that simply being in service is not a badge of honor if the next failure was built in during the installation phase. Precision maintenance isn't just about owning a fancy laser alignment tool. It is a quality system. Think of it as a series of controls designed to remove stress, friction, and uncertainty. We look at 5 pillars: support, geometry, force, cleanliness, and proof. A reliable machine isn't an accident. It is the deliberate output of a controlled, engineering-driven process. When we look at a machine train, we have to see it as a hierarchy of geometry. Every layer depends on the one beneath it. You can't perform a perfect alignment on an unstable foundation, and you can't expect clean oil to save a bearing that is being distorted by housing strain. We build reliability from the bottom up, starting with the load path and moving toward the operating baseline. The core argument of this presentation is that we must build reliability into the machine first, then prove what we've done. We follow a deliberate 5-step sequence. Stabilize the support, de-strain the components, align and balance the rotating elements, keep the system clean, and finally, prove the results with documentation. Let's start with step 1, stabilizing the support geometry. Step 01 is all about installing a load path that does not move. The integrity of the foundation, the grout, and the base plate determines whether your precision alignment will actually survive the first time you torque the bolts or start the motor. If the base isn't stable, the alignment is just an illusion. Foundation does much more than just hold the weight of the machine. It has both static and dynamic duties. Statically, it must prevent settlement and distortion. Dynamically, it must control motion and vibration without amplifying operating forces. We must verify everything from concrete integrity to natural frequency separation to ensure a solid foundation. When inspecting a foundation, remember that small defects lead to large uncertainties. We need to look for cracks, loose anchors, and grout voids. We also need to be wary of resonant supports. Sometimes high vibration isn't a balance issue, but a structural one. Map these defects before you even think about touching the shaft coupling. The load transfer stack must be continuous. Think of it like a bridge. Any gap at any interface turns a rigid machine into a spring-loaded one. From the sound concrete foundation up through the grout, the mounting pads, and the shim packs to the machine foot, every connection must be clean, flat, and fully supported. The golden rule here is to inspect before you correct. If you don't measure the support system before aligning the coupling, you're essentially providing a precise-looking wrong answer. Visual condition and anchor response are the ground truth that tells us whether our alignment data can actually be trusted. Now let's talk about soft foot. This is essentially machine frame distortion waiting to happen. When the feet aren't in the same plane, tightening the bolts forces the frame to bend to conform to the base. This distortion changes the internal geometry of your bearing housings, leading to premature failure. We must fix this before the final alignment. Diagnosis is key because not all soft foot is the same. Parallel soft foot just needs shims, but angular soft foot requires correcting the geometry of the pad itself. We also see induced soft foot from pipe strain and squishy soft foot caused by dirt or bent shims. Each requires a different surgical approach. Executing a soft foot correction requires a controlled sequence. You clean, loosen, and measure movement 1 foot at a time. Only after you've diagnosed the specific type of soft foot do you correct it and verify. This ensures you are restoring full, stable contact across the entire machine base. Even with a perfect soft foot correction, the machine can still be stressed by pipe strain. Alignment isn't truly complete until the piping, conduits, and ducts stop moving the machine. We have to remember, The machine is a precision instrument, not a structural support for the plant's piping. To verify pipe strain, we use a release connect measure process. We align the machine with the flanges released, then connect them using approved procedures and measure how much the shaft moves. Forced fit up is a defect, not craftsmanship. If the connection moves the machine outside of tolerance, the piping must be corrected. When it comes to the bolts themselves, torque is just an input. The real goal is joint preload. Factors like thread condition and lubrication can wildly change how much clamping force you actually get at a specific torque value. Never copy a torque value without understanding the assumptions behind it, such as the lubricant used. Controlled tightening is about managing how load is distributed across the joint. We follow a star or cross pattern in progressive passes, starting with a snug fit, moving to an intermediate load, reaching the target, and finishing with a final verification pass. This prevents uneven loading and distortion. Before we move to alignment, we must pass the first acceptance gate. This means we have physical evidence that the foundation, grout, anchors, soft foot, and pipe strain are all within limits. A green gate isn't a feeling. It's a documented fact that protects all the work we are about to do downstream. Now that we have a stable base, we move to step 02, alignment and balance. While alignment removes avoidable forces at the coupling, precision balancing controls the internal rotating forces that remain. Together, they ensure the geometry and the forces are in harmony. Shaft alignment is about controlling both offset and angle in the vertical and horizontal planes. A single gap reading at the coupling is insufficient. We need to understand the full relationship between the two shaft center lines to ensure they are collinear during operation. A common misconception is that a flexible coupling fixes misalignment. In reality, flexibility just protects the machine from immediate destruction. It doesn't make the misalignment free. Misalignment still generates heat, reaction forces, and wear. Flexibility is a safety margin, not an excuse for poor geometry. We also have to account for thermal growth. A machine that is perfectly aligned when cold may be significantly misaligned when it reaches operating temperature. We use cold targets, intentional offsets, to ensure that when a machine expands under load, the center lines converge exactly where they need to be. Alignment execution is a disciplined process. It begins with preparation and destraining before you even mount the laser. We then measure, diagnose the moves, execute the correction, and finally verify and document the report. This prevents the instrument from simply recording errors we should have already removed. Just because a laser displays a digital result doesn't mean it's valid. We must ensure mounting rigidity, avoid coupling backlash during rotation, and check for mechanical runout. Repeatability is the ultimate test. If you can't get the same reading twice, you haven't found the truth yet. When making corrections, we translate alignment data into specific shim changes and horizontal moves. Use clean jacking points and prevent rebound. The mantra here is predict the move, execute the move, and then remeasure to verify you achieved exactly what you intended. Sometimes the machine just won't move where you want it to. It's base bound or bolt bound. Don't try to force it with more torque. These are engineering constraints that require real solutions, like modifying support pads or repositioning the entire train, rather than heroic but flawed alignment attempts. Acceptance should be based on the most demanding applicable standard, not the most convenient number. Coupling limits are for preventing damage, but reliability standards, like ANSI or ISO, are for ensuring long life. Always document the as-left condition as the final proof of the bolted state. Next is rotor balance. Unbalance takes a tiny mass error and turns it into a massive rotating force that increases with the square of the speed. It's important to remember that alignment and balance solve different problems. Alignment fixes the path, while balance fixes the force of the rotor itself. To fix unbalance, we must match the correction to the pattern. Static unbalance might only need a single plane fix, while couple and dynamic unbalance require two plane corrections. Understanding the principal inertia axis is the difference between a successful balance and just chasing your tail. Balance quality is defined by residual unbalance, not just a vibration number. When specifying a job, you must consider rotor behavior, service speed, and the specific ISO 21940 quality grade required. Don't rely on outdated references. Use the modern standards that reflect current engineering best practices. In situ balancing, balancing in the field, is a controlled experiment. You must first confirm the unbalanced signature and rule out other faults like looseness. Then, you record a baseline, apply a known trial weight, measure the response, and finally calculate the permanent correction. When evaluating as left vibration, context is everything. One number doesn't fit all machines. We use ISO 20816 as a guide, but we must account for machine class, power, speed, and measurement location. A baseline without this context is effectively useless for future comparison. A critical warning: do not balance the wrong fault. High 1x vibration is evidence of a problem, but it isn't always unbalanced. It could be mechanical looseness, resonance, a bent shaft, or misalignment. If you add weight to a resonance system, you might reduce the amplitude, but you won't remove the cause. Step 03 moves us into lubrication cleanliness. We must treat lubricant as a precision component. The tight clearances we've worked so hard to create through precision installation can only be protected if the lubricant is the right product, in the right condition, and kept free from contamination. Precision lubrication is about three things: the correct product, the correct condition, and the correct quantity. Even the best oil will fail if it's contaminated with water or dirt, mixed with incompatible products, or delivered through a dirty funnel. Contamination control is a chain of custody problem. It enters through the handoffs we fail to control. We need a defined owner for cleanliness at every stage, from delivery and storage to transfer, dispensing, and finally inside the machine reservoir itself. A clean machine cannot be filled from a dirty lube room. We must identify and segregate products, use filtered breathers to exclude dust, and implement strict first-in/first out rotation. Regular audits of labels and housekeeping ensure that the process remains disciplined over time. Every lubricant transfer should be closed, dedicated, and filtered. The goal isn't necessarily a clean room, but a controlled path. Remember, a single dirty funnel could defeat a state-of-the-art bulk tank and filtration system. Keep every connector capped and clean. We measure cleanliness using the ISO 4406 code. This three-number code represents the concentration of particles larger than 4, 6, and 14 microns. For example, a code of 18/16/13 gives us a standardized way to talk about the health of our oil across different systems. Cleanliness targets belong to the component, not the oil drum. We define what is required based on OEM guidance and criticality. Then, we prove we've met it through calibrated particle counts and representative sampling. If you don't define the target, you can't control the outcome. When flushing a system, the clock doesn't decide when you're done, the evidence does. We define boundaries, achieve turbulent flow to mobilize debris, and sample until we prove repeatable cleanliness. Only then do we seal the system for final fill and startup. Precision greasing is a common area for error. More grease does not mean more reliability. We need the correct product, a calculated quantity, and a defined interval. Crucially, calibrate your grease guns by actual mass delivered, rather than assuming every pump is the same. Changing a lubricant is an engineering change, not just a brand substitution. We must assess compatibility between base oils and additives and plan the changeover to avoid leaving residual product. Once the change is made, we must update all records and monitor the machine's response closely. After commissioning, we must maintain cleanliness. Exclusion is always cheaper than cleanup. Using high-quality breathers, seals, and cap quick connect prevents the very contaminants that filtration systems are designed to remove. If we block the entry points, the system stays reliable. Step 04 is commissioning proof. This is where we start the machine deliberately and leave behind documented evidence. Commissioning is the final filter that converts all our installation controls into operating proof through readiness gates and as-left verification. Pre-commissioning begins while the machine is still safe to inspect. We verify rotation, lubrication, and interlocks before energy is introduced. The start button should be a gate to confirm what we already know. not a tool to discover if we forgot something. A mechanical readiness walkdown is essential. We use signed checklists to verify configuration, lubrication levels, fastener condition, and instrumentation calibration. Every exception must have a named owner and a plan before the machine is ever energized. The first energization is usually a bump test. This momentary start answers critical questions like rotation direction and abnormal sounds with minimum exposure to the equipment. We do this independently for drivers and driven equipment whenever possible before the final continuous run. We then move through controlled startup with planned hold points. We energize, idle to stabilize auxiliaries, step up the load, and eventually reach rated conditions. Only after the machine is stable and we've performed a final inspection do we establish the official operating baseline. An as-left baseline is only valuable if the context is recorded. A vibration or temperature number without the speed, load, and process condition is meaningless. We must document exactly how the machine was configured when the data was captured. Final acceptance looks at the machine as a whole system. Any red condition, like unresolved movement or high vibration, stops the turnover. Amber conditions need risk owners and deadlines. We don't accept the machine until the mechanical, lubrication, and protection domains are all verified. The as-left data package is the machine's reliability birth certificate. It contains everything: foundation records, alignment reports, lubrication evidence, and commissioning logs. This package preserves the knowledge of the machine's state for the entire life of the asset. Turnover governance ensures that operations accepts a defined condition. Turnover transfers ownership, but it doesn't erase defects. If the geometry is unstable or protection is unavailable, it is a no-go. We must be honest about the residual risks we are handing over. In step 05, we focus on operationalizing precision. How do we make this a standard way of working? We need job plans, competent people, and calibrated tools. The goal is to make the precision method easier to follow than the old shortcuts. A precision job plan controls the opportunities for defects. It includes prerequisites, clear execution sequences, and specific hold points for independent checks. It's not just a list of tasks. It's an execution package that demands as-left data and responsible sign-offs. Accountability must be clear. The executor measures, the verifier confirms, engineering defines the standards, and operations provides the stable state. When everyone knows their role in the decision-making process, the quality of work rises naturally. Your program is only as credible as your measurement system. Calibration is the bare minimum. You also need the right tool range, stable setups, and practitioner competence. If the measurements aren't reliable, the acceptance decisions won't be either. We track our progress with performance indicators. Leading signals, like the percentage of jobs with complete data packs, protect the process. Lagging signals, like a reduction in early life failures, prove that our precision efforts are actually paying off in the real world. If you're just starting, use a 90-day deployment. Spend the first month baselining critical machines, the second month standardizing your field procedures, and the third month piloting the program. Prove the benefit on a small scale before trying to roll it out across the entire plant. Let's look at a practical example: a pump train replacement. This isn't one job. It's one job with 7 distinct acceptance gates. If you fail gate 2, correcting soft foot, then gate 4, alignment is no longer valid. Success requires passing every gate in order. The business case for precision is simple. Preventing just one rework loop can fund the entire program. Rework isn't just about parts. It's about the massive costs of mobilization, production impact, and lost labor capacity. Precision protects your most valuable resources. Watch out for these implementation traps. Don't just buy a tool and expect it to solve your problems. Don't skip soft foot checks, and don't ignore the importance of raw data. Avoid expensive theater by focusing on controlled execution rather than just going through the motions. To continue your learning, I recommend these authoritative standards and practical resources: API RP686 for installation, ISO 20816 for vibration, and various guides from SKF and others for lubrication and alignment. These are the foundations of professional precision maintenance. As we conclude, I ask you to make a commitment. Stop accepting it runs as the definition of complete. A precision-maintained machine is stable, aligned, balanced, clean, and proven. Install the condition you want to operate. Precision is not perfection. It is controlled, repeatable evidence of quality. Thank you.